All right, let's get right into it. We're going to talk about one of the most persistent and honestly dangerous myths in engineering. This idea that if you make every single part of a system 99% perfect, the whole thing is going to be perfect too. But as you're about to see, that assumption, it's not just a little bit wrong, it's a guaranteed recipe for disaster.
I know. This sounds completely backwards. How on earth can being almost perfect guarantee that you're going to fail? Well, it turns out it's not a trick question. It's actually a mathematical certainty. Stick with me and we'll break down the surprisingly simple math that trips up even the sharpest program managers. Okay, so here's the absolute key to understanding this. The reliability of a whole system. It isn't the average of all its parts. No, it's the product. You actually have to multiply the reliability of every single component together. And that, right there, is where that comfortable feeling of safety just completely evaporates. Just look at how fast the numbers crumble. Let's say you have a pretty simple system, just 4 subsystems. Each one is tested and proven to be 99% reliable. That sounds amazing, right? But when you multiply 0.99 by itself 4 times, your total system reliability instantly drops to about 96%. You've lost almost 4% of your reliability right out of the gate, with components that are supposed to be nearly perfect. And this is where it gets really scary, because complexity is the true enemy of reliability. Let's just add 2 more of those 99% perfect parts. Now you're down to 94% overall reliability. You might think, a 6% failure rate, what's the big deal? But for a critical piece of hardware that needs to work for 10 years, that 6% gap means mission failures are not just possible, they are guaranteed. So this brings us to the big, flashing question. If every single component passes its individual tests with flying colors, what in the world is going on when we put them all together? Where does this disconnect come from? And the answer is a massive, fundamental blind spot in how we normally test things. See, we test components in a sterile, perfect, isolated little bubble, but we almost never test how they actually interact with each other, how they interfere with each other, and how they behave together under the intense stress of a real mission. We're testing for isolation, but the failures, they happen during integration.
So let's pull back the curtain and look at what's hiding in that blind spot. It turns out there are 4 major types of catastrophic failures that standard isolated testing is physically incapable of ever finding. And here's the thing. These 4 failure modes, they don't live inside any one component. They exist in the spaces between them. They're born from those messy, complex, unpredictable dynamics that only fire up when the whole system is running together under real-world pressure. First up, you've got something called common cause failures. So imagine a sudden, violent vibration or a massive heat spike. That doesn't just hit one part. It hits the whole system at once. And suddenly, components that have nothing to do with each other can all die at the exact same moment, all because they shared a common stressor that nobody ever tested for back in the lab. Next, you've got cascading failures. You know this one. It's the classic domino effect. All it takes is one component that's just barely operating within its limits. You put it under real stress, it finally gives out, and in failing, it overloads its neighbor, which then fails and overloads its neighbor, kicking off a massive chain reaction that can take down the entire system from one tiny starting point. Then there are interface timing mismatches. This is a subtle one. You can have 2 modules that work perfectly on their own. But when you plug them in together and start pumping real-time data through them at high speed, their communication just breaks. Signals get there a millisecond too late, data gets scrambled, and the whole system grinds to a halt because its parts are out of sync. And finally, maybe the most terrifying of all, redundancy switching failures. You know your backup systems, your fail-safes? They exist for one reason, to save the day when everything goes wrong. But the cruel irony is, they're often never tested under the exact same high-stress conditions that cause the main system to fail in the first place. So when you need them most, they don't turn on. So it all comes down to this. We've been chasing the wrong thing. The goal isn't to get 99% reliability for every little piece on a spreadsheet. The only goal that actually matters is mission success for the entire integrated system, when it's out there operating in the messy, chaotic, real world. So how do we actually do that? How do we hunt down these hidden killers before a mission is on the line? Well, the solution is a process designed specifically to attack that testing blind spot. It's called multi-level environmental stress screening, or ESS for short. You can think of it as a test as you build philosophy. It's brilliant, really. Instead of waiting until the very end to see if it all works, you introduce realistic stress at every single stage of assembly. You stress the circuit boards, then you stress the assembled modules, and then you stress the whole thing. You find the weak points right as they're being built. And it's a super logical progression. You start at the very foundation, the printed circuit boards. Then you move up a level to the integrated modules, and you finish with the main event, a full system shakedown of the complete final unit. And here's how it works in practice. At the board level, you might run extreme temperature cycles with the power off. Then, once you have modules, you hit them with intense random vibration from every direction. And finally, for the complete unit, you do it all at once. You blast it with heat, cold, and vibration. But this time with the power on and the whole system running. That is how you find those 4 hidden killers.
Okay, so we've got the problem and we've got the solution. But let's be real, running these kinds of defense-grade tests takes some seriously specialized equipment and know-how. This isn't something you can do in a garage. You need the right partner. And that brings us to B Analytic Solutions.
These are the folks who live and breathe this stuff. They provide this exact multi-level ESS capability. And when you see accreditations like NABL and DGQAI, I mean, those are massive seals of approval in the defense and aerospace world. It means they are a trusted authority. Plus, their labs run 24/7, making sure these critical systems get put through the ringer before they ever go out the door.
So the main takeaway here is pretty clear. It's time to stop chasing that illusion of 99% perfection for every little part. It's a number that feels safe, but hides catastrophic risk. If you want to ensure true mission success, you have to test the entire system under real-world stress. And if that's your mission, the experts at BE Analytics Solutions are the ones who can help make sure your system isn't just perfect on paper, but actually truly mission-ready.